Good morning, everyone, and thank you for joining me for this session of the conference. My name is Malcolm Calvert, and I'm joining you today from Northern Ireland, in fact, where I'm based for a couple of weeks, but I'm usually work in Scotland. I'm the Paramics Director for SYSTRA Limited. SYSTRA Limited is an engineering consultancy with a global reach, and one of the things that we do that's come out of our UK business is we've developed a traffic simulation product called Paramics, and my role is to oversee the development of that product. So this session today is all about the principles of traffic simulation and why traffic simulation is really useful and valuable in transport planning. So let me go straight ahead with the presentation. I thought I'd start with a quick video, because they say, you know, a picture tells 1,000 words, and often when we watch something and see it on screen, we really get a sense of it. And so what you're seeing on the screen at the moment is a traffic simulation. It's Paramics micro simulation, which we'll talk a little bit more about later. And so what we get with a traffic simulation is essentially a reflection of reality. This is what we're trying to do when we simulate traffic within a computer model, is we're trying to recreate what's actually going to be happening on the street, and then using that as a basis for decision making. So you can see with this interaction of vehicles in 3 dimensions, we really get a sense of how traffic behaves. So we'll go into how this actually works and why we use it through this session. So first of all, we might ask ourselves, what is a traffic model? Why do we do traffic modeling, and what are we trying to achieve? Well, there's a couple of definitions here which I think are quite useful. The first one says a traffic model is a tool for analyzing major ways people travel using a computer program. So there's a variety of software, of course, available to do these kind of things, but all of the software that does traffic simulation will have 3 key parts. The first one is a representation of the road network. So whenever we're creating a traffic simulation, we're always creating a specific place, a specific geography, and so representing that network, that geography, is really important. Another key aspect is some kind of socio-economic data. So how is that land being used? Is it a city? Is it a smaller town? Is it a rural area? Is it a link between 2 cities? There's all different kinds of ways that our places can be made up. And so we need to represent that within our traffic models. And the third key thing is then some kind of mathematical formula to represent the distribution of trips within that model, and we'll talk more about that as we go through. I like this definition from the California Department of Transport. It says simulation models are designed to emulate the behavior of traffic in a transportation system over time and space to predict system performance. And that's a really key part of the principles of traffic simulation, is giving us the ability to predict what is going to happen in the future, to test different assumptions and scenarios. Now, it's important to remember that traffic models they're a means for testing proposals and the effect of growing traffic demand in order to make decisions. So really, one of the key parts of them is you can test expensive ideas in a model, in a computer simulation, and rather than testing them by road construction, which of course is an expensive process. So by doing the planning and the simulation first, then we're going to be hopefully saving money and saving and making good decisions in the future. But they're not a substitute for decision making. We've always got to recognize that these are models, these are representations, and so they're not a substitute for the decision-making process. We've got to take them as one factor in that process. Now, there's two sort of broad categories of types of traffic models that are used in the transport planning industry And we could call these macroscopic models and microsimulation models. So the macroscopic tends to look at cumulative traffic stream characteristics. So that might be average speeds or flows or densities on a road network. And there's a couple of examples of products that use those. Now, microsimulation models, which is what I'm involved with and what my team developed with Paramics, they involve this dynamic modeling of individual vehicles and a representation of the complex interactions between them. So this type of modeling really became available in the late 90s when just processing power on computers and technology was able to represent these individual vehicles in a computer simulation. It's been developing over the last 20 years or so in these different products, which are now quite mature and able to model such a variety of different cases. So we're going to be looking a little bit more at microsimulation models as we go further in the presentation. Now, this is an example of a microsimulation model and the area that a microsimulation model covers. This was one that was developed by SYSTRA Limited. And the reason for showing you this is because when we talk about microsimulation, we're not necessarily saying it has to be a small model. The micro part of it refers to the fact that it's the individual vehicles that are being simulated, not that the network or the model is necessarily small. And as you can see from this image in front of you, you can get large microsimulation models, and this one is, sort of 20 kilometers square in area. And there's several models in Paramics of this type of scale. So let's look a little bit more deeply at how microsimulation actually works. So I'm going to play this movie for you. And in some ways, it's really simple. The simple way to think of it is as if you were the driver in a vehicle going through a network, and think about the kind of decisions that you would make as you drive through a particular network. So you're thinking about things like which lane you want to be in to get to your destination. You're thinking about the vehicle in front of you and how close you are to that vehicle or not. You're noticing traffic lights, signals, and you're stopping or going depending on whether those lights are red or green. You're thinking about gap acceptance and give way behavior. So at this example of a roundabout, as you approach, you'll be looking to see if there's a large enough gap to accept and to drive through and continue on your journey. So one of the things I love about traffic simulation and microsimulation in general is it's really easy to sort of put yourself into the scenario, because we will all have experience of using our transport networks, and many people have experience of driving and using the road networks behind a steering wheel in a car. And so it's quite easy to actually understand the kind of behavior that's going on. So let's dig a little bit deeper into how microsimulation really works. So I mentioned there that one way to think about it is how you would actually behave as you were driving through a vehicle network. So there's simple rules that are applied. Although it's a very complex system, the rules of behavior are actually quite simple. So one of the rules will be speed. What speed are you driving? And that really also applies to car following. So that you might be driving at the speed limit, but if there's a vehicle in front of you that's driving more slowly, then you'll be limited by that vehicle. So that's going to be one of the rules that guides you. There'll be a rule about lane changing and when it's appropriate to change lane, when there's enough space in the lane beside you to move into or not. Gap acceptance then is a key principle where one driver would give way to another driver. And this will happen at various junctions within our traffic networks. And then the fourth rule then is route choice. And let's explore route choice a little bit more. So a key question with route choice is, what is the best way to get home or to get to work? what is the best way to get to my destination? And that's how the vehicles within a traffic simulation model will work. We'll be thinking essentially those vehicles will be trying to choose the best option for them to get to their destination. And that option will depend on a variety of different things. It will depend on the time it takes to get to the destination and the distance. And those are things that are calculated within the traffic simulation. So the distance is obviously calculated by the road network and the different links that make that road network up. And then the time can be calculated by the speed limits on that road network, the likely delays at junctions, and also delay that might be caused by congestion. Then you've got the type of road. So if you've got a motorway or a highway, it's going to be a more attractive road than if you've got a narrow street which might have parking on it or traffic calming. So the type of road's important for your choice in destination. The traffic conditions are also important. So again, if there's a lot of congestion, it's going to make that less attractive. If the roads are clear, it will be more attractive. And then we also factor in just something about perception, because although the conditions might be the same, different drivers perceive things in different ways. So some drivers might see a particular route as a better way than another driver. And so we build in a little bit of variation around different drivers' perception of their routes. Now, the underlying principle in the majority of traffic assignment models is based around this idea of minimizing the cost of the journey. So it's the same thing as what is the best way to get home, minimizing the cost. I want to spend as little time or money on getting to my destination. And that's captured in this generalized cost equation where you've got a factor for time, for distance, and then also any extra costs. So if there happens to be tolls within the particular network that you're modeling. And then there's also these other aspects which play into the choice of routes. And within Paramics, we describe them as road hierarchy, vehicle familiarity, having different generalized cost equations for different vehicle types, perturbation, and dynamic feedback. And so the road hierarchy is actually being able to create and model the different types of roads, essentially, because we know that we will have a different grading of types of roads in our network, whether they be our highways or our sort of smaller and narrower roads. So we need to have a way of creating that. We also need to have a way of saying, well, which drivers on this network, which vehicles are familiar with the network, they know it well, they maybe have driven it, hundreds or even thousands of times, versus drivers who are there for the first time. They're maybe tourists, or they're just using this network as a through route. So some way of accounting for the familiarity of drivers is important. We talked about the generalized cost equation, and being able to set that for different vehicle types is important, because of course some vehicle types will value time more, other vehicle types will value distance more. So typically cars, those driving cars, are more time-based, and the heavier type vehicles are more distance-based. And so the ability to vary that's important. And perturbation, well, that's the term for varying the perception of costs that I talked about on the last slide. And finally, and a really important one, is dynamic feedback within a traffic simulation model. And that's the ability for drivers to reevaluate their routes as they go through, because conditions will change on the network depending on the time of day. So you might start your journey and there's a congestion in one part of the network, but as you continue your journey, the congestion moves to a different part depending on the time of day, and different things will impact congestion, like the commuting period of the day, or school opening or closing times, that type of thing. Now, another key part of microsimulation is traffic signals. These are kind of fundamental to any traffic simulation or microsimulation product. And so it's really important to be able to include these within the simulation. But in some ways, the rules are very straightforward with traffic signals. You've got red and green for stop and go, and then depending on which country you're in, you will have slightly different configurations of that. But we've also got the ability, and most traffic simulation products will have the ability to model quite complex signals. So signals which can optimize for the congestion, which can detect vehicles on the network, which can change at different times of day and be very flexible. And that's a really important part of micro simulation and traffic simulation, is that being able to model quite complex signal control. And so putting all these pieces together, where we've got our rules of the road network, which are to do with the speed that we're driving and the lane that we're choosing, or it's the route to our destination, or it's the use of signal control within the model. All of this has this kind of cause and effect process within a traffic simulation. So we might think of it as organized chaos. In one sense, what you can see when you look at the transport network is lots of small agents, lots of mini cars and drivers moving around this network, and it looks a bit chaotic. But there is order to it, there is a system to it, and there's a cause and effect process. And what's great about micro simulation is that you really get a sense of that cause and effect in action. And what I've learned over many years of using these types of models and working in this area is that you can sometimes be quite surprised by what an effect over here on your network might have over here. And so this slide shows an example in Scotland. This is beside Edinburgh, the capital of Scotland, where we developed a traffic simulation model of a lot of the motorway network in this area. So you've got lots of major roads. And what we found was that by an incident which happened where that blue arrow is on the Edinburgh City bypass would have a really significant effect where you see the red arrow, which is on a road called the A8. And so you wouldn't necessarily know that from a macroscopic model or from that kind of deterministic modeling. But what microsimulation can do is it can show you those cause and effect relationships. So as congestion forms, queues build back through the network, they affect a junction, and then that builds back and affects the next junction. So it's like this fluid, it's almost like fluid motion or fluid mechanics. Or you could always think of it like water in pipes as the traffic moves through the network and the different like ripple and knock-on effects that can happen. And the real value here of microsimulation is understanding those ripple effects, those network effects, and then being able to make adjustments to account for them to be able to try and reduce them. Okay, so hopefully that gives you a good sense of what a traffic simulation, what microsimulation is. So just a little bit about some of the modeling inputs that go into a microsimulation model. Now the system inputs, they don't differ that much from other traffic modeling systems, but the principal difference is you need to use smaller time intervals for collecting data and inputting it into the model, and also having a bit more refinement around the source of the trip demand data. So this is because when you're modeling at a microsimulation model, the time really makes a difference. And you'll probably know from your own experience, like traffic networks can change very quickly depending on the time of day, because the demand can increase. And so what we do with a microsimulation model is we profile traffic demand. So we get these peaks and troughs. And so when you're collecting data and inputting that into the model, you need to really collect those peaks and troughs in your data to put that in to create a robust traffic model. The trip demand matrices then is also a really crucial form in any modeling, and that doesn't really differ too much in microsimulation modeling. But having the information of origin and destination as much as you can be very useful. And then once the data is input into the model and the model has been coded and developed, then there's this calibration process which happens. And calibration is the process of then adjusting the parameters used in these various mathematical relationships within the model to reflect the data as well as necessary to satisfy the model objectives. So really what we're talking about here is we've got observed data from the real world that we've collected, where we might have collected junction turn counts or queue lengths or journey times. And then we've got our model, which we've created, and we're comparing one with the other. We want our model to be a really good representation of the data that we've collected. And calibration is tying those two things together so that the model is a really good representation. And then the validation process is an independent check of that calibrated model. So using some data, it's often journey times, to validate that the model has been well calibrated and is a good representation of reality. And once we've done that with a traffic model, once we've got what we would call our base model, or calibrated or validated model, we then got a really great baseline to then test all different kinds of scenarios within that system. Now, there are some limitations of traffic models. It's worth just touching on these. One of them is, of course, it's a representation. It's not an exact reflection of reality. We can't collect perfect data. And it is very heavily reliant on the input data that goes in. Traffic models cannot be more reliable than their data input. So they're always going to be as good as the data that you put in them, essentially. And oftentimes, planning authorities or those who are setting the budgets for these, they want to collect as little as possible because it can be costly and it can cause disruption. So it's a challenge for modelers to use the data set that they've got to try and create as good a model as they can. And then, of course, the big challenge is predicting traffic flows into the future. We know from worldwide over the last 2 years and everything that's been happening, predicting the future is very, very difficult. But what we have with our models is the ability to predict multiple futures. We can make assumptions about what if this happened or what if that happened. And we can look at a variety of different options to help us make good decisions about using our transport infrastructure. So what does microsimulation deliver? Well, it provides this means to really fully test the traffic flow responses to proposed network changes at a very detailed level. So it's a really, really good testing system for network changes. It also helps transport planners designing networks, so to come up with new ideas and test them really quickly. It's very good for traffic management schemes or signal control systems. And of course, one of the really powerful things about this, which you have seen from a couple of the videos, is the 3D visual graphics, which is brilliant for communicating what the model is saying. You also, of course, get really detailed numerical data out of the model as well, and you can extract that data. And it allows a variation in traffic flows and conditions to be accounted for. So each run of the simulation is just one sample. Our practice is to run these models multiple times so that you get lots of different scenarios run, and you get a real sense of like any variation within a particular design. So I've just got a few videos to try and illustrate some of these different benefits of traffic simulation and microsimulation. So this is an example of a motorway and what we would term an ITS system. So hopefully you can see there that the gantry where the speed limit has changed down to 50 miles per hour. And so all the vehicles on that network will now be driving slower. And the benefit of that is that as the vehicles drive more slowly, there's less risk of bunching of vehicles and shock waves on the network, and then lots of congestion and queuing on the network. So that's one of the things you can do in a microsimulation model. Another example is this one. This is a model of overtaking. So what you'll see as this model progresses is that the vehicles behind the heavy vehicle there, as another lane emerges, are able to pass that vehicle. And so we're able to actually model this kind of dynamic overtaking behavior and the benefits that come from adding in extra lanes to allow this type of overtaking in our modeling networks. Another example, this was reported in a major newspaper in the United Kingdom, where the testing was to look at using the hard shoulder of motorways as an extra lane in very busy times. And so this was something that traffic simulation was used to test before it was rolled out in practice. Another major project here, which Paramics was used for, was a motorway extension in Glasgow, which is the largest city in Scotland. And the new motorway was developed within the traffic simulation and then tested and modeled to make sure that the right number of lanes were being used, that all the junctions would work successfully, and so on. And this was a big project. Again, it's another one in Scotland, which is where we do a lot of our work. This was a new river crossing across the Forth estuary, a very significant project, which again, the microsimulation was used to test that it would work effectively. And another use of traffic simulation is large events. And this was the Olympic Games in 2012. This was the venue for the sailing competition in England, in a town called Weymouth. And what we're testing here is the increase in traffic that was expected because of the Olympic Games, which is obviously a very topical choice of video for this week with the Olympics happening in Tokyo. But it's very useful for testing event management. So when you're running a large event, you're obviously expecting a lot more traffic. Can the transport network handle that? What type of mitigation might be needed? What type of signage might be needed? Or public transport might be needed in order to reduce the private vehicle use on the network and that type of thing. So it's really, really good for testing and using in event management as well. And I think this is my final video. And this is just showing a light rail system running through a traffic network. So we focus mainly on the road network and the interaction of cars and other vehicles, but we can also model public transport. So whether it's a bus or a tram or a light rail system, you can see here, there's a light rail system going through this network, and we're able to simulate the interaction that has with the rest of the vehicles on that network. Okay, so that's the end of my presentation. I think I've just about come in on time. Thank you very much for listening. I hope that was interesting and useful. Introduction to the principles of traffic simulation, how it works, and some of the benefits of using this type of simulation as well. As I said, my role, my job is leading the development of Paramics microsimulation, which is one of these traffic simulation tools, and you can find out more about that through various links in this slide. We've also got a booth at the conference over these couple of days, so please feel free to drop in and say hello and ask any questions that you might have. Otherwise, it's just for me to say thank you very much for joining me today for this session, and I hope you enjoy the rest of the conference. Thank you.
Thank you very much, Malcolm. Thank you, and I'm sure that everybody got a very good idea of why simulations are important. That's what we have been we are trying to do as much as possible here in the region. As you know, we started our partnership a while ago, and it's very important for everybody to see and understand. So yeah, thank you very much. It was very, very helpful. I know that we will definitely be in touch and we'll be seeing each other soon again. But I also want to tell everybody to please go check the website of Paramics and the YouTube channel, where Malcolm has a lot of tutorials, a lot of things showing about the features and what is possible with Paramics. So please have a look at it, and yeah, we will see each other soon.
Thank you very much.
Thank you very much. Bye-bye.